the Galaxy architecture talks. Um, this time I'm going to talk about the pluggable components of Galaxy's backend. So during the models and managers presentation, I had this slide up, and it mentioned that managers are sort of the start, as you're coming from the API, the start of the interaction, corresponding to API requests, and models are sort of the endpoint, the thing that is sort of delegating access to the database. And I said there's a bunch of stuff in between, and these are just some examples. This set of talks is kind of this portion of the slides is my least favorite because I don't know how to organize it. Right? There's not really an architecture here per se. We have a big app object, and we just stick a bunch of other objects that do various functionality that comprise the backend onto it. And I've not really thought of a good way to sort of describe that or organize that. Sort of getting back to those principles, though, one thing that we do try to do is make sure that all of those things are as pluggable as possible. And so it's plugins all the way down. We've got some externally sort of defined or plugins. These are the WSGI middleware that we already talked about in the SQL Alchemy backends. Then we got some plugins that are just sort of plugins through inheritance. There's some base class that has some functionality, and we subclass it in various ways. And so this is a really simple form of plugin. The object store, workflow modules, tool classes, metadata collection strategies are examples of this sort of plugin structure. And then on these other ones, the custom and plugin config, there's more of a concept of like dynamic code loading. And so we have a sort of mini plugin framework inside of Galaxy called plugin config that I'll talk about toward the end of this that does this in a sort of structured and uniform fashion. And then we have a bunch of different places where we sort of do dynamic code loading that's a little more ad hoc. None of the framework around these plugins is particularly complicated, though. Ad hoc in the sense that like we just do it in, the most efficient way possible at that point in the code. So I think all of these kinds of sort of versions of doing plugins are fine. Plugin config has the nice attribute of feeling very simple and uniform. Inheritance, that is even simpler, right? If you've taken an intro programming course, you probably have an idea about how to plug in these things. But the rest of this talk, I'm just going to talk about a couple of different sets of these plugins and some of the context around them, for lack of a better way to sort of think about it. And hopefully, I'm covering important parts of the code base that are relatively complicated, or places you might, as a sort of external developer, be really keen on extending Galaxy in a specific way. So, yeah, I will talk about that. That's what I'll talk about. Sort of a very common place that you can extend Galaxy is by adding new data types. And to do this, we've got a class structure and then an XML file that goes along with the class structure. The data types are defined in lib Galaxy data types. The registry code is at the top, and what that does is that's going to read your data type comp for the one that Galaxy is deployed with. Load up the classes and definitions in there. The XML file describes like a short extension and then a base class that implements that. And so you can define new types by just saying use the same base class but subclass it dynamically, or you can actually fill out a Python class definition and get some real custom functionality. The base of all the data types is in data.py. There's a base data type. There's some simple text types in text.py, and the basis for the binary types are in binary.py. Other than this, most of the rest of the files in this directory are going to be sort of application-specific application-specific data types. So they are sort of grouping the data types by what kind of analysis they're useful in. What part of science? Hopefully we have some documentation somewhere that's more like of a tool developer centric kind of, because data types are this is something you really will very commonly want to do if you're building out a tool suite or something. Speaking of tools, tools are a big piece of the backend. A lot of code is dedicated to this. I want to talk about three big classes. The toolbox, tool, and tool action. So the toolbox contains tool objects that execute a tool action. And these are the packages they're found in: libgalaxy tool action, libgalaxy tools, and libgalaxy tools toolbox. Yes, let's go into. So the toolbox is the container object for tools. So when the process starts up, it loads up all the tools, and they're stored in the toolbox. The tool, there's one class that implements that most of the. So I say there's custom code here because there is an inheritance structure of different kinds of tools and different kinds of tool actions, but most of the special logic that makes up a particular tool is defined in an XML file. So it describes what command to run, what the inputs look like, etc. And I mean, all of that is writing a Galaxy plugin. So tools are a sort of interesting case because they're pluggable on multiple levels. You can have a regular tool with different tool actions. You can have a regular tool and just modify, just have a different tool XML file. It corresponds to a different object. Or you can customize the actual tool class. Here's some examples of tool classes. And so for the most part, this isn't something you would want to do if you're just deploying Galaxy and running tools from the tool shed. This is if you want to sort of extend Galaxy with some custom framework features. So a pretty common application of this are the database operation tools, which show up in the default tool panel as collection operations. Stuff like zipping, unzipping collections, merging collections, filtering, failed data sets, filtering based on a file, relabeling a collection. All these subclass tool because they don't really run external jobs. They have inputs and outputs like a normal tool, but they do operations on the database. An interactive tool is a class that's been added relatively recently. Dan Blankenberg added these with some help and presented them at the 2019 GCC. So check out his talk on those. They sort of these tools need to be run inside of a container, and the container exposes ports and gives them sort of an interactive experience for the runner of the tool. So IPython would be a sort of typical example of this. Expression tools are tools that use ES script or JavaScript to sort of modify just values in a workflow. So this is for like workflow logic sort of things. Data manager and data source tools are special tools that do interesting things with the outputs, and so they need the subclass tool. And the set metadata tool again it does special things with the outputs, so it has a subclass. In the past when I presented this, I got kind of tripped up, so hopefully when I try to describe what happens when you run a tool, so hopefully this diagram that I just made is helpful in some way, but because this is a relatively complicated part of Galaxy, and so this diagram looks pretty complicated, but it's hiding a lot of details still. So we have the client, and we're going to talk about two client calls the web form makes: build and create. And so these calls don't really deal with the models directly, and so there's no manager here. The tools controller, the tools API controller in libgalaxy, web apps, Galaxy API, controllers API, just sort of deal with the toolbox and tool directly. At some point in the future, maybe we'll put a manager in here. Probably would make some sense, but this is one of those examples where we don't do that. And so the two operations I'm going to talk about are rendering the tool form and submitting the tool form. So to render the tool form needs to know what the inputs are. It needs to know what the default values are. If there are values that depend on other values, maybe the build gets called multiple times, and like custom filters and stuff can be running here. So it's more complicated than it sounds. This isn't necessarily an endpoint that you would use if you're running like custom API calls, but it is a endpoint that the client uses, the web client. And so the first thing that the tool controller does is it takes a tool ID that's parsed from the request parameters, and it asks the toolbox, hey, give me the tool corresponding to that, and you get a tool object. And then it simply calls toJSON on the tool, but it's going to pass in some parameters here, presumably. And then it's going to get a dictionary back, and that's going to be sent back to the client. And so this dictionary will describe, what the inputs look like, how to validate the inputs, the labels, the possible values for data parameters, etc. The more interesting endpoint is then once that tool form is rendered and submitted, tools create is called. Now, just pointed out years ago that this isn't very RESTful. It should be creating a job. But unfortunately, it's the post on API tools that executes tools still, RESTful or not. And so when to run jobs, you do a post against API tool, and then create gets called. The same thing again. The controller will use get tool, the get tool method on the toolbox and fetch a tool, and then it will call handle inputs using that trans object that the web framework has given it, the incoming data parameters, the current history, etc. So more is happening here than just get the tools and handle the inputs, right? So like incoming is being processed, the history is sort of being discovered. Things are happening here. This is a very simplified view, but the handoff from the controller to tool is this handle input method. And so then that request might have like collection mapping steps in it. It might the API supports things that aren't even available in the client, like mapping over like non-data parameters. So like run a tool with different values of for a parameter, like different numbers for a numeric parameter, for instance. And so there's some complicated logic around running and creating all those jobs and figuring out which sort of output collections can be created and such. And so a long time ago, I made this execute.py file that tried to, encapsulate some of that logic. Unfortunately, writing it out to the diagram sort of makes clear where I sort of messed up and made this. I don't know. I don't know if this was a good design choice, because one of the first things it does is it calls back to handle single execution on the tool. This is, I don't know. As a software developer, I don't love this, even though I did do this. Execute, this tool class is just huge, and it's in a file that's huge, and I just wanted to separate that logic out, for better or worse. So I think the code looks a little cleaner, but clearly as a diagram, it's challenging. And so one thing that execute does, though, is it finds all the different mapped parameter combinations and starts looping over them to sort of execute a job for each of them. Now, executing that job is handled through the tool action, but to get there, we sort of call handle single execution back onto the tool. And so the tool will figure out what its action is, call execute, and the sort of typical tool action is gonna validate the input parameters, set up the output data sets, create output collections. Does the mapping job figure out where in the output object it needs to sort of seed its outputs. And it's going to do a bunch of work, a bunch of complicated work. It's going to tell the object store where, I need data sets created for this. It does all that work to get to a job object. And then it simply calls on app job manager, calls enqueue the job. It says to enqueue the job. So a lot of action is happening in here. Enqueue is relatively simple. It just puts that in the database and waits for a job handler to pick it up. But it sends the job and some outputs back. The job and outputs get back to execute.py, which is going to aggregate them. And then jobs are going to be sent back to the tool, and then back to the tool's controller, and back to the API call, and out to either the to the UI client or to the caller of the API caller. So that's some of the complication around tools. There's a lot more. Upload tools have a special custom tool action that handles, getting those files from the proxy into the rest of Galaxy, into Galaxy internals. So there's complicated tool actions. But there's other ways that tool can be changed. Model operation, database model tools, have different executes, etc. But this is the sort of typical usage. And so you might wonder then, I put the job in the database, then what happens? And so another complicated part of Galaxy that's pretty interesting, pretty central to what it does, though, are jobs. And so a little bit of jobs terminology here. The job is placed into the database and picked up by the job handler. So the job handler is in libgalaxyjobs handler.py, which actually delegates most of the work to job handler queue. But job handler queue watches the job and transitions to job state. And it handles figuring out which runner is needed to run the job and handling startup and finishing tasks. The job runner mapper decides a destination for a job. So the handler takes care of the waiting for the inputs to get ready, waiting for job limits to be such that the job can be run. But once the job is ready, it delegates off to the job runner mapper to sort of decide the destination for the job. And then a job runner, for instance, a drama job runner, actually runs the job and provides an interface for checking the status of the job. And so it itself has its own sort of polling loop. We'll talk about this. Here's just some examples. So there's another example of a pluggable interface with a relatively simple inheritance hierarchy, but it's listed in the custom code loading because these files are loaded by class name in the Galaxy's job configuration. So there's a base job runner, and most of them are asynchronous job runners. The one exception is the local job runner, and even that every day becomes a little bit more asynchronous. Yeah, and there's some examples. There's some very sort of long-running, like PBS and Condor job runners have been around forever. Drama job runner has been around forever. If you don't know what drama is, it's a common interface to interact with batch processing, sort of cluster systems. And the drama job runner can work with Slurm or different backends directly, but you can also adapt it with specific functionality for the runner you're targeting, or for the DRM you're targeting, the distributed resource manager you're targeting. So we've got specialties of this for Slurm, which we use on usegalaxy.org, and for Univa. A more exciting recent development that's been getting a lot of usage is the Kubernetes job runner, which talks to the Kubernetes job API. There are some other ones, but this is just the key files and the key classes, and these are all in libgalaxy jobs runners. Yeah. So I mentioned that job handler is a pretty interesting part of the Galaxy code base. So I just want to talk a little bit about, just give you some flavor for what happens in there. So when it starts up, when the job handler starts up, it starts a new thread that the job handler queue runs in, and monitor is called, and it just loops forever. And each loop, it loops and then sleeps and then loops and sleeps. So it will run while the monitor is running. Each time it calls monitor step, which is most of this diagram. And monitor step does two big things. It grabs the unhandled jobs and assigns itself as the handler for those jobs. So if you have multiple processes, the logic for figuring out which handler takes the jobs is going to probably be in grab unhandled jobs here, unless it was taken care of as part of the tool action. So we've got a lot of different options for how we handle jobs, but in a sort of simple case, they're just sort of assigned in this method. And then it handles the waiting jobs. And so what it will do is it will loop over all of the potentially ready jobs, and it will figure out which ones are actually ready. And I say that like it's a simple task, but it's not. So the most interesting SQL alchemy in the project, I think, is in the job handler file, because you got to make sure the dependent jobs are done. You got to make sure all the inputs are ready and populated properly. We support 6 or 7 different kinds of job limits, and you need to make sure all of those are sort of handled properly. And so there's a lot of logic that's happening inside handle waiting jobs here. But once you've sort of figured out based on the database, hey, these jobs look like they might be ready, there's still a whole other level of dynamicism where you can ask, you got to figure out what the destination is. And at that point, the admin may have custom rules. And the admin may say, well, the cluster is not in a position to sort of figure out where this needs to go yet. I'm not ready. And so the job wrapper is created for these potentially ready jobs, the ones where, you know, the handler at least thinks when it's time to assign this. And job destination is called to the job runner. And the job wrapper, to the job wrapper, not the job runner. The job wrapper delegates to the job runner mapper and says, give me a job destination for this. And so this is a place where an exception might be thrown. The job's not ready for some reason, and in which case, you know, it will skip this. And the user will be informed of what the dynamic job mapper said, the dynamic job destination code decided. But if a job destination is returned, then it's ready to go, and the destination is ready. At this point, put is called on the default job dispatcher, and the default job dispatcher's job is to just basically get the job to the job runner, the specific implementation. So the job destination is sort of queried, its runner parameter, its runner name is figured out, that plugin is found, the class, the implementation is pulled out, the specific object that is serving as the runner, and put is called on the job wrapper. At that point, the job runner is then responsible for the code. So I guess technically, I mean, I'm running out of time here, but the job runner should have another sequence diagram like this, where it's sort of checking the status of its own jobs. Then there's another interesting part of this code in the handler, where when the handler starts up, the jobs are fetched out of the database, and it's responsible for figuring out which runner it needs to use and give those jobs back to that job runner. So there's a lot of excitement happening in here, but most of what you would probably want to do is, if you're writing plugins for Galaxy or modifying Galaxy in some way, is a dynamic job destination, which we cover in the admin training, or writing a custom job runner. Again, sort of based on this inheritance and base class. A special kind of, there's a lot of different kinds of special tools and special jobs. One of them is data managers. Data managers are responsible for sort of populating Galaxy's tool data tables. And so if you see code inside of Galaxy for that, that's what it's responsible for. So the data managers tie together tool data tables, location files, and then the actual data files. And they're generally, though, if you're implementing a data manager, you're implementing something that looks basically like a tool. And you can check out the tools IUC for examples of this. Another pluggable piece of Galaxy is the visualization plugins. Adding a new visualization plugin to get a Galaxy instance requires some configuration file, generally XML, a base template, which is either Mako or JavaScript, and then some additional static data. This has changed a lot over the last year, and I realize now I didn't update the slides. So we're trying to get better sort of about not packaging the static metadata with the static data with Galaxy. So part of writing a visualization probably now is actually creating a node package.json file for it, so we can sort of build the visualization plugin as we're building the rest of the Galaxy client, and we can pack everything properly, and we're shipping less inside the code. But there is a tutorial on writing a visualization. So the packaging of these things probably has changed a bit, but I think the configuration of them and how they operate is still largely the same, if that makes sense. Here's an example of one that consumes a history data set. It can take these data types, and this is how it exposes it to this Mako. There's some visualization, there's some examples in config plugin visualizations. These are just a couple different ones from sort of least complicated to most complicated. Chemical structure view and GraphViz are relatively simple visualization plugins. Charts is its own separate plugin framework itself. And then Trackster was the original plugin example, and it's so integrated with Galaxy's code, it's almost not even proper to think about it as a plugin. Hopefully one of these examples, or just looking at the examples inside of charts, these are even more modern. You can just implement a chart instead of a full visualization. That's even better. But that's one way to extend Galaxy. If these visualizations need to consume Galaxy data in some sort of interesting way, slice and dice it, based on data type or based on some algorithm, some way of accessing the data. That's what data providers are for. I haven't actually seen a data provider added to Galaxy in years, so I don't know that this is very common. But maybe if people were writing more visualizations, I actually don't know, because we've gotten visualizations, but they generally seem to not require interesting views on Galaxy's data. But if you do need that, data providers are a way of doing that. Yeah. It's adapting the raw data set to the API, basically. Yeah. Slice, filter, reformat, etc. And I think these are shipped in with the data types. So I think you would write custom code and stick it in the libgalaxy data types data providers. Interactive environments. So we mentioned interactive tools, which are a special kind of tool that sort of corresponds to a container. Interactive environments are a special kind of visualization that correspond to a container. So interactive environments have been around a little bit longer, but I think the consensus is slowly forming around interactive tools being the way forward for interactive analysis in Galaxy. But some slides here. There's a tutorial. The thing about interactive environments being a bit older means the documentation is a little bit more evolved. Some examples that we ship with. We also ship with a bunch of examples of interactive tools. And that is a lot of the plugins. That's the visualization piece. Again, it's just a bunch of different plugins, but we will press on. Another one is the object store. So we try, the dataset object has a file path. We try not to write to it directly because we're trying to get away from assuming the files exist on the file system. And in fact, we have. I shouldn't say we try. We have done this. So rather than sort of Galaxy framework code doing stuff like this, all access to Galaxy datasets, to the contents of Galaxy datasets, should be sort of mediated via the object store. So update from a local file, fetching the data, fetching a part of the data, etc. So the object store is responsible for all of that. And the reason that the object store is responsible for all of that is so that we can have interesting different backends like S3 or iRods where the data doesn't need to exist on the disk. Some of the methods in the object store are they're exactly what you would think they are. Is the data, does they exist? Create a new object for me, get the size, delete it, and and then update it, essentially. The disk object store is the simplest one, just a directory on the file system. And iROD's object store is a special kind of that that uses the iROD's API. In 2020 here, Kayvon has doing an awesome job, and we're feeling better than ever about the iROD support in Galaxy, and we're slowly transitioning usegalaxy.org to use an iROD's backend. S3 is a little bit older, very commonly used though. And then we have some sort of meta object stores. So these are nested object stores that sort of combine multiple configurations, right? So if you have some legacy data that you want to keep available to Galaxy, and then you have some other data, and then like a new file system that you want to write new data to, you can use a hierarchical object store. So, if it's not available in the new one, check the old one, but write everything to the new one. That sort of logic is encoded in the hierarchical object store. The distributed object store is, if you have a couple different systems and you want to just distribute the data across them. And that's object stores. And in terms of plugins, this is just a simple inheritance, really. I mean, implement the interface, find the one that seems closest to it, extend it, modify it. From a plugin perspective, it's relatively simple. Another relatively simple plugin structure are the workflow modules, and these are so simple they're all in one file. They have Galaxy workflow modules, and these are basically the implementation of the logic for the node in the workflow editor graph, right? And so most of these are going to be, in the typical workflow, most of them are tool modules. It says run a tool. But there are different kinds of inputs. For a long time, they're just data sets, and then we added collections. And then this last year, we've really been pushing, parameters, like formalizing the data type for the inputs to workflows and providing a sort of better user experience around that. Sub workflows were added in 2016. And the pause module is an example that we don't really expose in the user interface, but it shows what some of the sort of backend scheduling framework is capable of. So we can pause a workflow and wait for some API requests and then continue the workflow. That sort of logic is possible with workflow modules, but we haven't really done a lot with that in terms of the editor and user experience yet. The workflow module, unfortunately, since it does so much, is quite complicated and quite dynamic. A couple static methods from dict and from workflow step basically build the module either from a database object or from the workflow source or an API source. Get tool state, get export state. These get basically the contents of the step as a sort of dictionary. The contents, basically the stored contents, versus runtime state, which is, a description of what is needed to actually run it, what needs to be executed at runtime. So this, maybe one way to think about the export state is the defaults, and runtime state is well, if you're overriding the defaults, what do those look like at runtime? So an input, for instance, has relatively simple export state. You might say the format, but the runtime state then is going to be the actual file that's picked. That's an imperfect description of it, but that's some of the ideas. Since these are nodes in the graph, they have inputs and outputs, which are dictionaries. Even this complicated set of methods here, which I'm having a hard time explaining, is only a subset, and is a simplified subset of what's in workflow module. Every couple years, we sort of rewrite the workflow modules. The good thing is that there's just the 7 of them, but that's what that looks like. So I mentioned that there's this plugin infrastructure in Galaxy that a lot of different components use, and it's a standardized way to both load the plugin class implementations from a directory of Python files, but also to parse either XML or YAML descriptions of the configured plugins. And so these provide a very consistent interface for both the developer and the admin. because anything that's configured this way has a very simple and a very simple XML format that is easy for admins, and a very simple YAML format, and Galaxy can read either for any of the plugin types, even if we don't document it. That's not true. But like the framework itself, at least, is capable of handling that. And so I'm going to go through a simple example here based on container resolvers. So the core framework code is in libgalaxy-util. It's plugin config.py, and it heavily uses submodules py in the same file. And the particular example I'm going to talk about is in tool-util depends. So tool-util deps. Containers has a registry of the configured plugins, and the actual implementation of the plugins is in container resolvers. And there's two implementations in there's multiple implementations, but there's two files that contain implementations for container resolvers. Something like dependency resolvers have a lot more files associated with it. But this is a relatively simple example. And then the configuration is read from config container resolvers conf.xml.sample. But it can be whatever you want in Galaxy YAML. You could even, I think, probably embed it directly in the YAML itself, if it's a YAML description. So plugin config, the first thing it does when you write a registry using it is to create a dictionary of the plugin configurations. And so this is done with plugins dict. And so what it does is it imports all the submodules of the configured module. So in this case, it would be that container resolvers. And so it's going to load these two. It's going to loop over these two. It's going to load all the classes it finds that look like modules, and we'll talk about what makes that. And it's going to read the plugin identifier. So we'll look at an example, but I think for these ones it's resolver type. So it's going to be all the classes that have a resolver type and are listed in the file manifest, essentially. The underscore underscore all underscore underscore. I don't know what it's called in Python, but the description of the classes in the file. So it's going to loop through these submodules, find all the classes, and then read this plugin type and add it to a dictionary. And so we've got a simple way to go and figure out all the different resolver types for everything in that submodule. So the container registry. So this is an example of the registry of the containers that are configured, the container resolvers that are configured, that uses that plugin config code, right? And so the first thing it does, in this sort of simplified, you can look at the actual file. It's a little more complicated than this, but first thing it does is it loads those definitions for the plugin classes. App info is like I tend to try to get away from Galaxy's big global app object and global config object by writing the subcomponents so they have a specific interface onto that big global mess. And so app info is the container app info, everything that the system probably needs to figure out how to resolve containers for Galaxy. And then it's going to build the container resolvers that correspond to that application information, which includes the configuration of Galaxy. So building that, we're first going to do is we're going to find the configured configuration file that we're going to load the plugins from, the configured plugins from, and then we're going to use plugin config to sort of build a plugin source. So it turns this path into a source. And so we have this plugin source. It's just a little tuple, and the reason we do this is because we could load them from a file or we could load them from a dictionary directly. And so the plugin source can sort of encodes either. And then we call parse resolver conf here, which is going to call the load plugins method from that framework code. And all it needs is that plugin source, the resolver classes that we loaded with plugins dict, and then whatever extra keywords we're going to use to initialize each plugin with, each configured plugin with. So some of the keywords that will be used to configure the plugin will come from the plugin description file, but some are sort of global things that all the plugins will get. And in this case, the thing that we're sending every plugin is the app info. So this is its sort of interface to the rest of the galaxy. Here's a little example of one of the resolvers that's in mold.py. With a typo, this should be tabbed in, of course. So it's called the cache mold Docker container resolver, and it's a container resolver. And here's where you can see that's getting app info in its constructor. So there's a plugin implementation. And then these two things are things that you can configure in the file. And we'll see what the files look like, but you can specify namespace in that file, and you can specify a hash function. And then all it does is it sets up those two things, and then when resolve is called, it just does its magic. And so resolve would somehow be figured out from the containers code, right? So this registry, in this case, this registry is probably going to call resolve, probably has a resolve function or something that's going to call the resolve of the plugins in turn. So again, we've got namespace and hash function 2, and then we can see what the actual configuration files look like. And they're quite simple, and you can sort of, the XML and YAML map pretty directly to each other. The XML has a root document. Probably the framework code is not going to look at what's in this tag. So, I mean, this could say John Rocks, and that would probably be fine. But it's going to assume it's a list of plugins, and it's just going to load the plugins in order. And so here's the default configuration, and here we've modified that namespace to be my custom. And so the framework code is responsible for getting this namespace from the XML file into the abstract description and then passing it to the actual plugin. Same two plugins configured in the YAML. We don't need this list thing. We don't need this root wrapper in the YAML. We can just call the resolver type is cache mold in both cases, and then the namespace in the second case where we want to pass in custom parameters. And so you can sort of see why for modern plugins I've been pushing the YAML more, because this then can be a dictionary of things. It can be a lot more complicated, which is nice, without needing custom XML parsing. And so if we go back, anyway, let's see. I'm trying to, we can't go all the way back to those slides, but some of the examples of things that are configured this way include like tool errors, authentication is configured this way, job metrics are configured this way, container resolvers, tool dependency resolvers. So there's a good number of plugins that are configured this way. If you're thinking about adding a new pluggable framework to Galaxy, hopefully you look at plugin config and use that to provide a really smooth interface. All right, that's that.